a fit. So kind of the history of chi-square tests. Walter Frank Raphael Weldon was an English evolutionary biologist and a founder of biometry. He was the joint founding editor of Biometrica with a man named Francis Galton and Carl Pearson. In 1894, he rolled 12 dice 26,306 times and recorded the number of 5s or 6s, which was his success. It was observed that 5s or 6s occurred more often than expected, and Pearson hypothesized that this was probably due to the construction of the dice. Most inexpensive dice have hollowed out pips, and since opposite sides add to 7, the face with 6 pips is lighter than its opposing face, which only has 1 pip. Right? So you've got the die. Right? So if the 6 lands face up, then the 1 lands face down. And so if the dots or the pips on the die are hollowed out, this has more bits hollowed out than this, and so the 1 is going to land face down and the 6 lands face up. Or at least that was his hypothesis. 9, Zachariah Labby from the University of Chicago repeated this experiment using a homemade dice-throwing pip-counting machine. So if you click through to the YouTube link, see if it'll actually play for me. So here he's got a machine that bounces the dice. And then he's got, I think, 12 dice at a time. And then he's got a webcam on top that takes a picture of the dice and then uses computer AI to count the number of pips. I don't understand exactly how it counts it, what they did there exactly, but uses AI to count what shows up on the dice rather than having to count it by hand, which is really cool. Anyway. So, this process took about 20 seconds per roll, which was about 150 images to process manually each day. But at this rate, Weldon's experiment was repeated in a little more than 6 full days, whereas it took him a couple of years to do it. And so Labby did not actually observe the same phenomenon that Weldon observed, higher frequencies of 5s and 6s. This, by automating the process instead of doing it by hand, Labby was able to collect more data than Weldon. So instead of recording successes, which Weldon said was a 5 or a 6, and failures, 1 through 4, he recorded the individual number of pips on each die. So we got the number of, for the number of rolls for each number. And so this is a graph of his data. And what you see is that he got more 1s and 6s and fewer of the numbers in the middle. So he rolled 12 dice, 26,306 times. If each side is equally likely to come up, how many 1s, 2s, etc. would he expect to have observed? Right? There's a 1/6 probability of getting each number. He rolled 12 dice, 26,306 times. That's D, whatever that turns out to be. 52,612. Right? So here's the observed and the expected counts from his experiments. Yes. So 52,612 is the expected for each one, and there's his observed counts. Right? And so you notice that the 1s and the 6s are higher than the expected, and all of the rest of them are lower than expected. So the expected outcomes are all the same because each number has a 1 in 6 probability. So on average, we would expect to get the same number of counts for each number. So we want to know, do these data provide convincing evidence of an inconsistency between the observed and the expected counts? Our null, right? Null is always the status quo. There is no inconsistency between the observed and the expected counts, or the observed counts follow the same distribution as the expected counts. Our alternative is that there is an inconsistency between the observed and the expected counts, that the observed counts do not follow the same distribution as the expected counts, or there is a bias in which side comes up in a roll of the dice. Okay, so to evaluate these hypotheses, we quantify how different the observed counts are from the expected counts. Large deviations from what would be expected based on sampling variation or chance alone would provide strong evidence for the alternative hypothesis, right? We expect a certain amount of sampling variation just due to chance. But something that deviates very far from that variation that we would expect due to chance would give us evidence in favor of the alternative hypothesis, that in this case, all numbers on a die are not equally likely to come up. And so this is called the goodness of fit test, since we're evaluating how well the observed data fit the expected distribution. When we're dealing with counts and investigating how far the observed counts are from the expected counts, we use a test statistic called the chi-squared statistic. That is the Greek letter chi. Chi-squared is the sum of the observed counts minus the expected counts divided by the expected. Observed minus expected squared divided by the expected counts. We do that for every category that we have, and then we add them all up. All right, so calculating the chi-squared, we would do 53,222, that's our observed, minus our expected, 52,612. We square that and divide by 52,612. So the next one would be 52,118 minus 52,612 squared divided by 52,612. 52,465 minus 52,612 squared divided by 52,612, and so on. And so you would do all of those, and then you would add them all up, and that'll get you your chi-squared statistic. So why do we square it? Squaring the difference between the observed and the expected outcome does two things. One is that any standardized difference that is squared will now be positive. Otherwise, we would have the same number of negatives as we would positives, and they would cancel out and we would get 0, which is not useful. The other thing is that differences that already look unusual will become much larger after being squared. All right, something that is very far away from the expected value is going to have a bigger impact on our chi-squared than something that is very close to the expected value. And you remember where we've seen this before? When we do our, when we do our standard deviation formula, right, it's the sum of the x bar minus xi squared over, when we do that, right, we subtract the mean minus each individual value, and then we square it. And that's why we always get a positive standard deviation, right? So that makes all of our numbers positive and also means that the more extreme values have a larger impact. So similar to the standard deviation formula. So that gives us a number for the chi-squared statistic. But in order to then make a determination about whether to reject or not reject the null, we need to know what the chi-squared distribution looks like. The chi-squared distribution has just one parameter, the degrees of freedom, just like the t-distribution has degrees of freedom, which influences the shape, center, and spread. Right? So this is what your chi-squared distribution looks like. At 2 degrees of freedom, it's going to be this. 4 degrees of freedom, it's here. 9 degrees of freedom, it's here. As the degree of freedom, the center of the chi-squared distribution increases as well. That's true, right? Here, your center was here. Here, your center is going to be more like here. So from 4 to 9, your center, in this case, your mean, is increasing as well, or your median. The variability of the chi-squared distribution increases. That is true. As you can see the data are more spread out at 9 compared to at 2. So the variability increases. And the shape of the chi-squared distribution becomes less skewed. Right? This is the one that's not true. It becomes more normal looking. So again, compare the 4 to the 9. The 9 is more normal. So as your degrees of freedom increase, your chi-squared distribution becomes less skewed, more normal. So back to Labby's dice. Do these data provide convincing evidence of an inconsistency between the observed and expected counts? Our null hypothesis was that there was no inconsistency between the observed and the expected counts, that the observed counts followed the same distribution as the expected counts. The alternative was that there is an inconsistency between the observed and the expected counts. The observed counts do not follow the same distribution as the expected, or there's a bias in which side comes up in the roll of a die. So, if you plug in all of those numbers from that table, and you do the observed minus the expected, and you square it, and you divide by the expected, and you add them all up, you get a chi-squared statistic of 24.67. I did not do all of that by hand because it was a huge pain, but you'll just have to take my word for it. Or you can go back and look at the part of the video that showed the data, and you can do it yourself. So, once we know, all we need to know now is the degree of freedom, and we can have a calculator calculate the tail area, or the p-value, and then we can use that p-value to make a decision about the hypotheses, just like we do with a regular hypothesis test. When conducting a goodness of fit test to evaluate how well the observed data follow an expected distribution, the degrees of freedom are the number of cells minus 1, right? Number of cells or categories, right? We had 6 categories, the numbers 1 through 6 on the die. So our degrees of freedom, 6 minus 1 is 5. So then we can do the p-value. So this would be approximately what the chi-squared distribution looks like for 5 degrees of freedom. And 24.67 is way out there. So for a chi-squared distribution, the p-value is the area in the upper tail only. You're always going to be shading the upper tail, right? Because the chi-squared is never negative. So you're always, that's one of the things, when we squared all of those values before we add them up, we make sure that our chi-squared is never negative. So we're always looking for something more extreme. In this case, that's always going to be the positive side. So in your calculator, if you go to distribution, you have something called chi-squared CDF. That's what we want. And we put in the chi-squared value that we got, which in this case is 24.67. We're always doing the upper tail, so we do 1e99, and then put your degrees of freedom in. And if you do that, in this case, 1.61 times 10 to the negative fourth, which is 0.00061, which is very small. At an alpha equals 0.05 level, right, this would be less than alpha. So at an alpha equals 0.05, we reject the null and say that the data provide convincing evidence that the dice are biased. It turns out that Welton was wrong about the pips. The reason why is that dice are not perfect cubes. The 1 to 6 axis is consistently shorter than the other two, which means that the faces that have the 1 and the 6 on them, and this picture is not right because the 1 and the 6 should be opposite. But the faces that have the 1 and the 6 on them are larger than the other faces. If the axis, right, if I've got dice, and this is the 1, and so the 6 would be on the back there, right? This axis is shorter, meaning that the other faces that have that as a side are smaller compared to this, which is going to be a square, and the 2, 3, 4s, and 5s are going to be slightly rectangular and a little bit smaller. This does not support Pearson's claim that the 5s and 6s appear more often due to the carved out pips. It could be that his dice were different, or it could be if he was only counting 5s and 6s, the fact that there were more 6s, there were enough more 6s to make it seem like more successes than failures. The dice used in casinos are very precise, perfect cubes. They have flush faces, so that the pips are not hollowed out, and they are precisely balanced and tested to be perfectly fair. Casinos do not like people to cheat. So the p-value for a chi-squared test is the tail area above the calculated test statistic. So this is your chi-squared value, whatever you got when you added everything up, and we always are finding the upper tail. This is because the test statistic is always positive. Higher test statistic means stronger deviation from the null. Conditions. Independence. Each case that contributes a count to the table must be independent of all the other cases in the table. Usually we're going to check random and 10% for independence. And then our sample size, our large counts condition is that each cell, each particular scenario, must have at least 5 expected cases. And your degrees of freedom must be greater than 1, which means you have to have more than 2 cells. If you had more than 2 cells, you would do a difference of means or a difference of proportions instead of a chi-squared. So you got to have more than 2 categories. If you don't check the conditions, then your probability of making a type 1 or a type 2 error may increase. Sometimes in class, we do things even if the conditions are not met for learning purposes. But if we were doing that in a formal environment, if you were writing a research paper, you would at the very least need to note that your conditions weren't met and explain why you think you can do the test anyways. In 2009, ye olden days of 2009, there was a lot of talk about election fraud in the Iranian election. So here they polled 504 people and asked them who they were going to vote for. And then we got the reported percentages in the election. All right, so this is our observed count. It's the poll data. Our expected distribution is what was actually reported in the election. So our null hypothesis is going to be that the observed counts from the poll follow the same distribution as the reported votes. The election was not rigged. The reported votes are the same as what was actually, what people intended to vote. The alternative is that the observed counts from the poll do not follow the same distribution as the reported votes. So first we need to find the expected numbers. With chi-squared, you can't use expected proportions, you have to use expected numbers. So we're going to do 0.6329 times 504 and get whatever we get for that. 0.6329 times 504, 318.98. I feel pretty comfortable calling that 319. All right, and this would be 0.341 times 504. 341 times 504. Which is 171.86. And this is 0.0261 times 504. 261 times 504, which is 13.15. Oh. Those would be our expected counts. And so if we do these, we do the chi-squared is going to be the observed, right? It's the sum of the observed minus the expected squared. Squared over the expected. So 338 minus 319 squared over 319, which is 361 over 319, which is 1.13. And then this would be 136 minus 171.86 squared for 171.86. calculator's causing me problems here. And so then that part is 7.48, and then he observed here was 30, and this was 13.15 over 13.1 squared over 13.15. It's 13.15 squared over 13.15, which is 21.59. If we add all of those up, that ends up being so carry your 2, 5, 7, 11, 12, carry your 1, 8, 9, 10, 11, carry your 1, 31.20. And so then we would do a chi-squared, we would do chi-squared CDF of 31.20, 1E99, and our degrees of freedom, we've got 3 categories, so our degrees of freedom is 2. And when I do this, I get I get 1.68 times 10 to the negative 8th, which is very, very small. Our p-value is low, our null is rejected. The observed counts from the poll do not follow the same distribution as the reported votes. The election was probably rigged. And that's it for chi-squared goodness of fit. Tune in next time for homogeneity and independence.